Welcome to this explainer. I am absolutely thrilled you're joining me today because we're looking at a topic that honestly feels a bit like a superpower. We are going to explore how engineers actually command electricity to make decisions at the literal speed of light. Let's figure out how we transform dry Verilog syntax into an incredible toolkit for building complex digital hardware systems. Okay, let's dive right into this with something we all use every single day. Think about your home setup. You might have an MP3 player, a laptop sound card, a satellite receiver, and digital cable TV, and they're all feeding into one surround sound system. So how exactly does the speaker know which audio to actually play? Well, it uses a multiplexer, often called a mux, acting as a selector. By just changing a tiny 2-bit signal, we can route any of those 4 unique inputs to the single destination. And this is exactly why we need to learn routing code in Verilog. Because without it, our digital systems would just be a chaotic, completely unusable traffic jam of signals. Here is our roadmap for today. We're going to start with the conditional operator, move on to routing with if-else, scale things up to the case statement switchboard, learn how to handle don't cares, and finally, wrap up with automating with for loops. Kicking things off with section 1, the conditional operator, or what I like to call the micro decision. So here is the absolute baseline of logic routing in Verilog. It all comes down to a question mark and a colon. It works like this. The code evaluates the conditional expression first. If that condition evaluates to a 1, meaning it's true, we choose the first expression immediately after the question mark. But if it evaluates to a 0, meaning it's false, we simply skip over to the other side of the colon and pick the second expression. It's an incredibly fast, lightning-quick 2-to-1 choice. Now, you might be wondering how this micro decision actually builds a physical 2-to-1 multiplexer. Well, we can use this conditional operator in a continuous assignment. If the select signal is 1, our output gets the first input. Otherwise, it gets the second. But we can achieve the exact same hardware result using a procedural statement inside an always block. The really cool takeaway here is that whether you use continuous assignment or an always block, this single, simple line of code physically routes the electrical signals based entirely on that micro decision. Moving right along to section 2, routing with if-else, the structured fork. Now, what's really interesting to note here is the evolution of our code. We have our super compact one-line conditional operator, sure, but compare that directly to the block-based if-else structure. Inside the always block, we're explicitly saying if our select signal equals 0, output the first signal, else output the second. For a simple 2-to-1 multiplexer, yeah, it takes a few more lines to write, but it gives us this highly structured, readable block that becomes absolutely critical when our hardware designs inevitably start to scale up. And this is exactly what scaling up looks like. This logic defines a 4-to-1 multiplexer, and notice just how cleanly the if-else structure handles it. Our select signal is now a 2-bit vector. We're checking it against specific binary values. If it's binary 0, 0, we route the first input, else if it's 0, 1, we route the next, and so on down the line. It's incredibly logical, incredibly easy to read, and acts as a perfect structured fork in the road for all our electrical paths. Bringing us to section 3, the case statement switchboard. Let's be real, when you have a massive list of possibilities, stacking else-if statements over and over again gets really messy really fast. Instead, we use the case statement. You just provide an expression to check and then list your alternatives. Now, the absolute crucial rule here is that the statement associated with the very first match is what gets executed. And please, look at the default clause at the bottom. This is so critically important. If your alternatives don't explicitly cover every single possible variable state, you absolutely must include a default clause to tell the hardware what to do. If you forget it, you're going to get some wildly unpredictable behavior. To really appreciate the sheer power of the case statement, consider the 4 to 16 binary decoder. We aren't just talking about abstract theory anymore. This is a massive, real-world switchboard. It takes a 4-bit input and decodes it into 16 distinct outputs. This exact kind of logic is used in memory systems right now to identify CPU locations. It selects functional units inside microprocessors, and it directs signals to different physical rows of memory chips. It's essentially the main traffic director for your computer's brain. And this brilliantly illustrates the sheer physical scale of that decoding. Just look at the nested circuit blocks required to distribute these signals. And the truth table alongside it shows how those 4 input lines map perfectly to 16 completely distinct output paths. Can you imagine writing a massive chain of if-else statements for 16 separate conditions? It would be exhausting. But a case statement handles this elegantly, matching the input directly to its corresponding output line in a snap. Let's move to section 4, handling don't cares, or as I call it, the messy realities of hardware. So, in Verilog, it isn't just a perfect world of ones and zeros. We actually have two other states, state X and state Z. Think of state X as the rebellious teenager of the circuit. It simply doesn't care if it's supposed to be a 0 or a 1. Its value literally doesn't matter to the final outcome. State Z, on the other hand, is high impedance. Think of Z as completely checked out. It acts like an open circuit and isn't connected to any defined voltage level whatsoever. Because hardware engineers encounter these indifferent or disconnected states all the time, Verilog gives us specialized variations of the case statement to write safe logic efficiently. We use case Z when we want the hardware to treat all those high impedance Z values as don't cares. And case X takes it a step further, telling the system to treat both the disconnected Z values and the indifferent X values as don't cares. This allows the code to just ignore them completely when searching for a match. A perfect real-world example of putting these don't cares to work is inside a priority encoder. This logic indicates the active input that has the highest priority. Let's say input 3 has the absolute highest priority, and it gets triggered, maybe by a critical system emergency interrupt. At that moment, the system literally doesn't care what the lower priority inputs are doing. Once that top priority input is asserted, everything below it is ignored, allowing the hardware to immediately act on the single most important signal. Finally, we reach section 5, automating with for loops. So the crucial point here is how we use an integer loop control variable to generate huge swaths of logic without having to type it all out manually. The syntax follows 3 basic steps. First, you set the initial index, that's your starting integer value. Second, you define the terminal index, which tells the loop exactly when to stop iterating. And third, the increment specifies how the variable changes each time. By placing our logic routing inside this loop, the hardware compiler does the heavy lifting, automatically stamping out the complex routing circuitry for us from start to finish. We started today looking at a simple MP3 player audio selector using basic multiplexers. But take a second and look at the device you are watching this explainer on right now. It contains billions of transistors, and they are all governed by the foundational microdecisions, conditional operators, case statements, and automated for loops that we just covered. So it leaves us with a truly mind-bending thought. If a few lines of code can route a simple audio signal, how exactly does an automated compiler scale these exact same rules to route billions of microscopic paths simultaneously? Think on that. Thanks for joining me, and I'll catch you on the next explainer.